So our next problem here is to find the general solution of this second order linear non-homogeneous differential equation. And the first thing we notice is that we have to apply the variation of parameters method. The reason we have to do so is because this external function here, e to the power t over t squared plus 1, has an infinite number of linearly independent derivatives. And because it has an infinite number of linearly independent derivatives, we can't apply the method of undetermined coefficients to solve this problem like we did in the previous video. So the formula for the variation of parameters is written here, where the particular solution y to this differential equation is equal to minus y1 multiplied by this first integral plus y2 multiplied by this second integral. If you notice here, we have the Wronskian of y1 and y2. So we have f of t times y2 over the Wronskian of y1 and y2. And in this second integral, we have f of t times y1 over the Wronskian of y1 and y2 again. So our first step here is going to be to solve for y1 and y2. y1 and y2 make up the homogeneous solution to the differential equation. They make up the solution to the homogeneous differential equation. So we have to solve for the homogeneous solutions. Once we find the homogeneous solutions, we take their Wronskian and we find their Wronskian so that we can apply them in these integrals. So once we have the Wronskians of the two homogeneous solutions, then we simply apply the formula here, which is just to evaluate these two integrals. So let's begin first by solving for y1 and y2. So if we apply Euler's method, then we can find that this differential equation becomes, well, let's first propose the solutions to this differential equation. So we propose that y is equal to e to the power rt. So we are going to insert this solution into the homogeneous version of this differential equation. So this solution here is going to be substituted into the homogeneous version of the differential equation. Right, y double prime minus 2y prime plus y equals 0. So after we insert this proposed solution, we find that r squared minus 2r plus 1 is equal to 0. Okay, and we can write this as r minus 1 squared is equal to 0, which gives us the double solution r equals 1, r equals 1. Now, because we have a duplicate solution here, we can write that our solution, remember we made the guess that y equals e to the power rt. So we can write the solution that y1 is going to be equal to c1 times e to the power t, because r equals 1. And for our second solution, we can say y2 is equal to c2, but this time, since we have a duplicate solution, we have to multiply the e to the power t that we're going to have here by an extra t. The reason we do this is to make sure that our second solution is linearly independent from our first solution. So our y1 is c1 times e to the power t, and our y2 is c2 times t e to the power t. So we can go ahead now and try to solve for the Wronskian between y1 and y2, which is the second step. So our Wronskian of y1 comma y2 is going to be the determinant, let's see, y1 prime, y2 prime. And this is going to be, if we make the substitutions of y1 and y2, this is simply going to be e to the power t and its derivative e to the power t. And the second entry is going to be, let's see, for y2 we have t times e to the power t, and then its derivative is going to be e to the power t plus t times e to the power t. So this is the determinant that we have to calculate here. Notice that we didn't include these coefficients, these arbitrary coefficients. And the reason is because once we calculate the Wronskian and we insert it into this formula here, right, because we have y1 and y2 already involved in the formula, all the coefficients are going to cancel out. Okay, so which makes sense because the particular solution never involves any arbitrary coefficients. So you don't need to include the coefficients when calculating the Wronskian. So we can go ahead and find this Wronskian to be e to the power t times e to the power t plus t times e to the power t, right? We multiply this entry by this entry and then subtract the product of this entry and this entry. So we're going to have minus t times e to the power 2t. So of course, once this e to the t distributes into this quantity here, we're going to have this term and this term cancel out, which leaves just e to the power of 2t as our Wronskian of t. So we can place this Wronskian into the formula here to solve for yp, since we have y1 and y2 and the Wronskian of t. So here we can say that the particular solution is equal to minus y1. y1 is just e to the power t. Remember I said we can neglect the coefficients because they're going to cancel out anyway. So y1 is e to the power t, so minus e to the power t times the integral of f of t, right? Our f of t was, let's see, e to the power t over t squared plus 1. So our f of t is e to the power t over t squared plus 1, and then multiplied by y2. So y2 is t times e to the power t. So times t times e to the power t dt. And then plus the second solution, y2. So y2 is t e to the power t times our integral e to the t over 1 plus t squared plus 1, and then multiplied by y1, right? The first solution, which is just e to the t dt. Okay, so this here becomes, of course, I forgot to put the Wronskian. We have the Wronskian in the denominator, so the Wronskian is e to the 2t. So I should include this down here and down here, right? So in this integral here, we're going to have an e to the 2t in the numerator, which cancels out with this e to the 2t in the denominator. So this cancels out. And over here, we have another cancellation with these two e to the t's here. So let's see, our particular solution, we can write it as yp equals minus e to the t times the integral of t over t squared plus 1 dt, and plus te to the power t, and let's see here, times the integral of 1 divided by t squared plus 1 dt. So the first integral is very easy to handle here. This integral here just becomes 1/2 ln of t squared plus 1 if you do a u substitution here. So this becomes minus 1/2 e to the power t ln of t squared plus 1. This is yp. In fact, let me use a parentheses here, t squared plus 1. And this integral here, if you recall the identity of 1 over t squared plus 1 integrated, we have a, let's see, let me use a different color here. We have a tangent inverse of t. So this integral here becomes tangent inverse of t, which means our solution is this term plus t times e to the power t times the tangent inverse of t. So we can write our full solution now. Since we have the particular solution here, our full solution is then y of t is equal to y1, which is c1 times e to the power t, and then plus y2, which is c2 times t e to the power t, and then plus our particular solution here, which is going to be minus a half e to the t ln of t squared plus 1, and then plus t multiplied by e to the t, so t times e to the t times the tangent inverse of t. And this is our general solution for the differential equation.